Hi everyone, for our final project for assignment 2, we focus on the movie length 1 million dataset. This data originates from group links research at the University of Minnesota and was collected from real users of the movie lengths recommendation platform. It represents a snapshot of approximately 1 million ratings from 6,040 users on roughly 3,700 movies. Some important facts to consider on this dataset is that these ratings are on a 1 to 5 star scale, meaning the dataset captures direct user feedback rather than the indirect signals like clicks or viewing behavior. So, in order to pre-process this data, we first handle the raw format. This dataset comes in a .dat file using a non-standard double semicolon separator. We parse this using Python's engine and handle the Latin 1 encoding to ensure all movie titles were loaded correctly. As noted in the code above, we also perform immediate feature engineering. The raw data provided age and occupation as cryptic code. We map these to human readable strings. For example, we converted occupation 4 to college student. This step allows us to create an interpretable demographic visualization later in the analysis. Now, heading down to dataset and summary statistics. When we initially looked at the dataset summary statistics, we see that the data sparsity is 95.74%. This is important because even though 1 million ratings sound like a lot, this percentage reveals that the user item matrix is actually 95% empty. Also, looking at the average rating of 3.58, we see that the data is centered at 3.0, indicating a clear positive bias. From this insight, we know that we immediately can use any dataset methods or simple classification method. Essentially, we are trying to complete a puzzle where 95% of the pieces are missing. This gives us insight in what sort of models we would like to use that are specifically designed to infer hidden preferences in a highly sparse environments. So, taking a look at the rating distribution, um, as noted on this histogram, this data is not uniformly distributed. Like we mentioned earlier, there's a clear positive bias with the distribution being heavily skewed towards the right. Because of this, the ratings form a positively skewed distribution, reflecting the tendency of users to rate movies they already expected to enjoy. In practice, people generally choose to watch movies that they believe they will like, rather than ones they anticipate disliking, which naturally leads to a higher average rating and fewer extremely low scores. As shown in the graph above, the rating across the entire dataset was a 3.582 with a standard deviation of 1.17 and a median of 4.0. This reinforces the idea that the rating scale was used more for expressing approval than disapproval. Users weren't just randomly rating everything, they were selective, engaging with content they had a positive inclination towards too. Now, taking a look at the genres of the movies, so beyond just numerical ratings, we also look in the content of the movie themselves. Looking at the genre distribution as noted in the graph, we see that the dataset is heavily dominated by drama and comedy, followed by action, thriller, and so on. So this context is important to us because it helped inform a modeling strategy. While we could build a content-based recommender systems, using features like this, we decided that due to the high data sparsity, capturing latent user behavior would be more powerful rather than relying on broad metadata tags, such as genres of movies. So now taking a look at age distribution and average rating by age group, we now shift our focus from the movies to the users themselves to identify any potential biases. In this dual axis plot, the green bars represent the number of users, while the teal bars represent their average rating. You will immediately notice a massive imbalance in volume. This dataset is heavily dominated by the 25 to 34 age group. The 56 and plus demographic is much smaller in comparison. However, when we look at the behavior, we see a trend. Despite their small numbers of the 56 plus demographic group, they have significantly higher ratings on average compared to the younger groups, even though there are few older users. The unique rating pattern gives us this insight for including user bias terms in our model. If we treated everyone as the average user, we would underpredict ratings for older users and overpredict ratings for younger ones. Now let's take a look at user demographics. So we see a similar pattern when analyzing gender. In this plot, the blue bar illustrates that the dataset is heavily male dominated. However, looking at the red dots relative to the green dashed line, which is the global average, we find that female users tend to rate movies above the global average, and male users tend to rate slightly below the global average. So therefore, if we ignore this distinction, our model might systematically underestimate how much female users enjoy content, giving us further insight to use specific users' bias terms in our models. So now taking a look at sparsity and long tails, we would look at the two charts above. So first looking at the ratings per movie, we see a long tail distribution. On the far left, we have the head, which is the movie that everyone watches. But looking how fast it curves down, we have the vast majority of 3,700 movies sitting in this queue, having very few ratings. This is important because using a popularity baseline will fail for 80% of the catalog, as noticed in the long tail distribution, so therefore we need to work with models that can infer preferences for niche content. Also, we see the exact same pattern in user activity. The histogram is heavily skewed. The vast majority of users have rated fewer than 50 movies, since both users provide very little data. Methods that rely on finding exact neighbors will struggle, so as noted above in the bar chart.
Moving on to the next section, identifying the predictive task you studied. Based on the EDA findings, specifically high data sparsity, which is 95%, and the nature of ratings, we're able to define our rating predictive task. Because the data set is so sparse, we can't classify this as a classification problem where we have dense features for every row. Instead, we formulated the predictive task as a matrix completion problem. Our goal is to infer the missing entries in the user item interaction matrix, with our input being a user ID and movie ID. And our output is a predicted rating on a scale from 1 to 5. For our evaluation metric, we use root mean square error. We chose this over accuracy because in recommendations, the magnitude of the error matters. Predicting a 4.8 for a 5-star movie is a success, whereas a strict accuracy metric will mark it as a failure. Also, compared to mean absolute error, root mean square error penalizes large outliers, forcing our model to avoid terrible predictions. To assess the validity of our models and prevent overfitting, we split the dataset into an 80% training set and a 20% test set. Furthermore, we set 3 baselines to serve as our sanity checks. We have the global average, predicting the mean rate, which is predicting the mean rating, which is 3.58 for everything. This sets our absolute our MSE to be 1.12. If our model can't beat this, then it isn't learning anything. Our second baseline is the user average, which predicts a specific user's personal mean. This lowers root mean square to 1.04. We included this to test how much individual users' pessimism or optimism affects the score. Last but not least, our baseline 3 is bias only model, which combines the global average, the user bias, and the item bias, which achieved a root mean square error of 0.9384. Why did we pick these baselines? The reason why we picked these baselines is because it represents the limit of simple statistics. It accounts for the fact that some users are grumpy and some movies like Star Wars are universally popular. These serve as our baselines. If our complex machine learning models cannot beat 0.938, it means they aren't capturing any personalized interactions, just general popularity. Moving on into our next section, our models. We start We start with an intuitive approach, which is the user-based collaborative filtering. On the code you see here, we encapsulated this logic in a class. We have the fit method where we pivot the training data to create a dense matrix where rows represent users and columns represent movies. We then calculate the cosine similarity between every single pair of users, allowing us to create a map of who is similar to whom. For the predict function, we implement a weighted average mechanism. For any given user and movie, the model looks up the k most similar users who have actually rated that specific movie. We calculated the predicted rating based on their similar scores, weighted by how similar they are to our target user. We also built a safety check for the cold start problem. If a user has no neighbors who have seen the movie, we fall back to returning the global average rather than crashing. Also, because this memory-based approach is computationally expensive, we evaluated on a subset of the test data, which resulted in an RMSE of 0.9833. This is actually worse than our simple bias baseline, which confirms our hypothesis that finding reliable user neighbors in a 95% sparse data is extremely difficult. Moving on into our next model, we flip the problem with an item-based collaborative filtering. Instead of looking for similar users, we look for similar movies. You can see the key change in the fit method. We pivoted the matrix so that movies are the rows and users are the columns. This allows us to calculate cosine similarity between items. The prediction here is that an item's rating profile is more stable than a user's rating profile, but users change their taste or rate inconsistently. The prediction logic remains similar to the user-based model using a weighted average of the k nearest neighbors. However, if a user wants to rate Toy Story, we look at what they rated other movies that are similar to Toy Story, like Aladdin or The Lion King. These results reaffirm our prediction. As you can see here, the item-based k-nearest neighbors achieve the score of an RMSE or root mean square error of 0.925, significantly better than the user-based model. Moving on to our third model, which is matrix factorization. We moved on from a memory-based method to a model-based methods with standard matrix factorization. Instead of just calculating similarities, we are now decomposing the interaction matrix into two lower dimensional matrices P for users and Q for items. In our code, we initialized line factors with random noise. We explicitly included BU for user bias and BI for item bias to ensure that our model learns the global offsets we identified in our EDA. We trained this using the stochastic gradient descent. As you can see in the loop, for every single rating, we calculated the error between the actual rating and our prediction. We then updated our user and item vectors by moving them in the opposite direction of the gradient. We applied regularization terms controlled by the reg parameters to prevent the model from overfitting to the training noise. Something important to note that we also did was that we mapped the user and movie IDs to continuous zero index range. This allowed us to ensure that our arrays are memory efficient and indexable. As you can see here, our model achieved an root mean square error of 0.9113. Lastly, put it here. We implemented our last model, SVD++. The standard matrix factorization only looks at the explicit rating, but by using SVD++, it adds a third vector, self.y. Scroll down a bit more. Which allows us to capture implicit feedback. This vector represents the influence of a user simply by interacting with an item, regardless of the rating. In the training loop, scroll down a little bit more. In the training loop, for every user, we calculated some y, the sum of implicit factors for every movie they have ever rated. This creates a user representation that is much more impactful than a single vector. We also updated the y vector during backpropagation, which the loop iterates through the user's entire history for every training step, making the model computationally expensive. It took us about 40 minutes to train, but it allowed us to fill in the blanks for users who provided very few ratings. As you can see here, our SVD++ model achieved our lowest test root mean square error of 0.8901. Next, going into our evaluations section, Before looking at the final test results, we needed to verify the training stability of our most complex model, SVD++. As we mentioned earlier, SVD++ is computationally expensive because it updates the implicit history vector for every single rating. To manage this for a demonstration, we limited the training to 5 epochs. As you can see in the plot, the training R root mean square error drops monotonically from 0.9529 in the first epoch down to 0.8754 in the fifth. As you can see from the illustration, the curve is smooth and steep, which is exactly what we want to see. This shows that our stochastic gradient descent is successfully navigating the lost landscape and finding a local minimum without oscillating or diverging. It also confirms that our learning rate of 0.01 was tuned correctly, which is fast enough to learn quickly but small enough to remain stable. Finalizing all our models, we illustrated in the chart, as you can see here. On the left, which is the gray colors, these are our baselines that set the standard. And the middle, the blue one, the neighbors models. And we noticed that the user base is 0.988, which actually performed worse than simple bias baselines, which confirms that due to 95% sparsity, finding reliable user neighbors is mathematically difficult. We have item-based k-nearest neighbors, which received a score of 0.92, which fared better, proving that item correlations are more stable. On the right, which we have the red ones, are our lightning factor models. We have the matrix factorization achieving a score of 0.91, which outperform all neighbor methods by learning hidden features. And our best model, SVD++, achieved the lowest error of 0.89. Sorry. This result proves that for sparse data sets like movie lens, simply matching users based on ratings k-nearest neighbors is insufficient. By using SVD++, we successfully incorporated implicit feedback, which is the user's viewing history, to build a richer user profile. This allowed us to improve upon the naive baseline by over 20%, providing a robust solution to the co-star problem, which we identified in the start of our EDA.
So now, after doing all the analysis, now we would like to go back to our discussion of related works. So, given that the movie length 1 million dataset has been one of the most widely used benchmarks in recommended system research, we have seen many studies that have used it to test collaborative filtering methods because it has real users rating, demographic information, and a high level of sparsity that reflect real world recommendation problems. Nevertheless, prior work on movie length's 1 million dataset has been primarily focused heavily on traditional collaborative filtering, such as user-based methods, which find people with similar rating patterns, while item-based methods find movies that are rated similarly by users. These approaches typically reach root mean square error values around 0.090 to 0.95, but they struggle with the dataset's high sparsity and long tail distribution, given that many users and movies have very few ratings. Finally, we must contextualize our results within the broader field of the recommended system research, or in this case, research done on this 1 million dataset. Historically, the movie length 1 million dataset has been the battleground for moving from memory-based methods like k-nearest neighbors to latent factor models. Prior work has established that neighborhood methods typically hit a performance ceiling around a root mean square error of 0.092 to 0.95. However, looking at results, this confirmed this theory exactly. Our item-based k-nearest neighbors plateaued at around 0.092, unable to overcome the data sparsity of the 1 million data set, which was 95%. However, work done by Netflix Prize by Corin suggested that in order to break the 0.09 barrier, one must account for implicit feedback. And looking back at all the results in our data that we achieved from these methods, it only validated this theory even further. So, by implementing SVD++, we achieve a root mean squared error of around 0.8901. Therefore, because of this, we are consistent with the state-of-the-art benchmarks for non-neural models on the dataset. Not only does it confirm that the significant computational cost of SBD++ is justified, but also its ability to model the long tail of users' behavior that simpler models might miss in some of the process of filtering out this data set. So that's it for our presentation. Hope you guys enjoyed it, and thank you.